What if the most famous rocks ever collected by human hands have been quietly rewriting the story of the moon for over 50 years now, and most people alive today have no real idea it ever even happened? Not a hidden chamber, not a secret discovery buried in a vault. Something far stranger, sitting in plain sight the entire time, inside sealed containers of gray lunar dust that Neil Armstrong and Buzz Aldrin carried back to Earth in July 1969. For decades, scientists believed they understood exactly what those samples were telling them. Whole careers were built studying them. Entire chapters of planetary science textbooks were written based on what those first analyses seemed to confirm. Then, using instruments that didn't even exist when the samples were collected, researchers went back and looked again. What they found didn't just add a new detail to the story of the moon. It challenged assumptions that had stood, mostly unquestioned, since before Apollo 11 ever left the launch pad. This is the story of what Apollo 11 actually brought back, why it took decades to understand what those samples were truly hiding, and why parts of that mystery still haven't been fully solved. To understand why this discovery mattered so much, you first need to understand what scientists expected to find on the moon before Apollo 11 ever launched. By the late 1960s, the leading scientific model of the moon's formation suggested it had formed through an incredibly violent, high-energy process, likely the result of a massive collision between the early Earth and a Mars-sized object, sometime in the first 100 million years or so after the solar system formed. This impact, according to the model, would have vaporized enormous amounts of rock and thrown molten debris into orbit around Earth, material that eventually cooled and coalesced into the moon. An event that violent, scientists reasoned, should have burned off almost every trace of volatile material, elements, and compounds with low boiling points, especially water. If the moon really formed from debris flung out of a catastrophic, high-temperature collision, it should be bone dry, essentially sterilized of water and other volatile compounds from the moment of its creation. This wasn't a minor assumption. It became one of the foundational expectations, shaping how an entire generation of scientists interpreted every rock and soil sample returned from the lunar surface. This idea, now generally known as the giant impact hypothesis, wasn't the only theory scientists had considered before Apollo. Earlier in the 20th century, some researchers proposed that the moon might have formed alongside Earth, condensing out of the same original cloud of material at roughly the same time, almost like a sibling planet forming in parallel. Others suggested the moon might have formed somewhere else entirely in the early solar system, and later been captured by Earth's gravity as it passed close enough. Neither of these alternative models gained the same lasting support as the giant impact hypothesis, largely because they struggled to explain certain details about the moon's composition and orbital characteristics that scientists had already begun measuring using data gathered from early robotic missions and ground-based observation. By the time Apollo 11 was preparing to launch, the giant impact hypothesis had become the leading explanation among planetary scientists, even though at that point it remained largely theoretical, built on mathematical modeling and indirect evidence rather than direct physical proof. Apollo 11's primary scientific goal, beyond simply proving humans could safely land on and return from the lunar surface, was to gather the kind of direct physical evidence that could finally test this theory against real material, rather than simulations and calculations alone. When Apollo 11 landed in the Sea of Tranquility on July 20th, 1969, Armstrong and Aldrin spent just under 2.5 hours outside their lunar module, collecting nearly 50 pounds of rock and soil samples using tools that, by today's standards, look almost primitive. A simple scoop, tongs, and a rake designed to sift smaller rocks from the lunar dust. They worked quickly, aware of limited time and a mission profile with almost no room for error, gathering material from the surface around their landing site without the luxury of carefully selecting each individual sample the way later missions eventually could. The samples themselves were far from glamorous to look at. Most of what Armstrong and Aldrin brought back was gray, fine-grained lunar soil called regolith, mixed with fragments of basalt, a type of volcanic rock also common on Earth, formed billions of years ago when ancient lunar volcanoes released huge floods of molten rock across the moon's low-lying plains, the same dark, flat regions early astronomers mistakenly named seas, or Maria, believing from a distance that they might be bodies of water. There was nothing about the sample's appearance that suggested they were about to challenge some of the most fundamental assumptions in planetary science. They looked, to most observers at the time, exactly like what everyone expected the moon to be made of: dry, ancient volcanic rock and dust. Once those samples reached Earth, they were distributed to laboratories around the world for analysis, and the early results seemed to confirm exactly what scientists expected. Using the technology available in 1969 and throughout the following decades, researchers tested the Apollo 11 samples for water content and found essentially none. The numbers matched the violent formation model almost perfectly. The moon, it seemed, really was as dry as scientists had predicted. For nearly 40 years, that conclusion remained essentially unchallenged, taught in textbooks, cited in planetary science papers, and treated as one of the settled facts of lunar science. The moon was dry. The Apollo samples proved it. Case closed. Except it wasn't closed. It just hadn't been reopened yet. In the early 2000s, a new generation of laboratory instruments began reaching a level of sensitivity that older equipment simply couldn't match. Techniques like secondary ion mass spectrometry allowed researchers to detect and measure incredibly tiny concentrations of elements and compounds, amounts so small they would have been completely invisible to the instruments available when the original Apollo samples were first analyzed decades earlier. To put the difference in sensitivity into perspective, the instruments used in 1969 and throughout the following decades could typically detect water only if it made up a reasonably significant portion of a sample's overall composition, the equivalent of trying to find a handful of sand mixed into a swimming pool. The newer generation of instruments developed decades later could detect water present at concentrations measured in mere parts per million, the equivalent of finding a single grain of that same sand somewhere within an entire freight train's worth of material. That leap in sensitivity didn't just improve the accuracy of existing measurements, it opened up an entirely new category of questions that simply couldn't have been meaningfully asked before, because no instrument existed capable of returning a reliable answer. Rather than collecting new samples, which was impossible since no human had returned to the lunar surface since 1972, scientists did something almost as remarkable. They went back to the original Apollo samples, material that had been carefully stored and preserved by NASA for over 30 years, and ran them through instruments the original researchers could never have used, because those instruments hadn't been invented yet. In 2008, a team of researchers re-examined tiny volcanic glass beads found within the Apollo 11 samples, tiny droplets of ancient lunar magma that had cooled and solidified almost instantly after being ejected from volcanic eruptions billions of years ago, trapping whatever gases and compounds were present inside the magma at that exact moment, like a bubble frozen in glass. Using their newer, far more sensitive instruments, the team detected something the earlier analyses had completely missed: water. Trapped inside the volcanic glass, at concentrations low but absolutely real, and completely inconsistent with a moon that had been fully sterilized of volatile material during its violent formation. These tiny glass beads, some smaller than a grain of sand, formed during what scientists call fire fountain eruptions. Violent volcanic events in which molten rock was ejected explosively from the lunar interior, flying through the near-total vacuum of the moon's thin exosphere before cooling almost instantly into small, smooth droplets of glass. Because that cooling happened so quickly, on the order of seconds, rather than the slow cooling process that shapes most volcanic rock on Earth, whatever gases were dissolved in the magma at that exact moment often became trapped inside the glass, sealed in place before they had any real chance to escape. In effect, each bead functioned like a tiny time capsule, preserving a small sample of the moon's interior chemistry from the exact instant of a volcanic eruption that occurred over 3 billion years ago. This finding alone was enough to genuinely surprise much of the lunar science community. But it was only the beginning. Over the following years, additional studies using similarly advanced techniques found trace water not just in volcanic glass beads, but bound within mineral structures throughout multiple Apollo sample collections, including material originally gathered by Apollo 11. Some studies even suggested that water might be more widely distributed throughout the lunar interior than anyone had previously imagined, challenging not just a single data point, but the broader model of how the moon formed in the first place. If the moon's formation had truly been violent enough to boil away essentially all volatile material, as scientists had assumed for decades, how could measurable amounts of water still be trapped inside rocks collected from its surface, sealed away since Apollo 11 first brought them home in 1969? This is where honest science requires slowing down, because the discovery of trace lunar water didn't hand scientists a simple, tidy explanation. It handed them a genuine, still active debate. One leading explanation suggests that while the moon-forming impact was indeed violent, it may not have been quite as thoroughly effective at eliminating volatile material as earlier models assumed. Under this view, some water may have survived the impact and the moon's subsequent formation, becoming trapped deep within the lunar interior during the process, only later making its way into the volcanic material that eventually cooled into the glass beads scientists analyzed decades afterward. A second explanation focuses on what happened after the moon initially formed, rather than during the impact itself. According to this theory, much of the water discovered in lunar samples may have arrived later, delivered by comets and water-rich asteroids that collided with the moon's surface over hundreds of millions of years following its formation, gradually depositing trace amounts of water that eventually became incorporated into the moon's volcanic activity and, eventually, its interior geology. This delivery theory gained additional support from a separate, related line of research. When scientists compared the specific chemical signature of water found in the Apollo lunar glass beads to water from various potential sources, including different types of meteorites, comets, and even water found in Earth's own oceans, They found the closest match came from a particular category of ancient meteorite called carbonaceous chondrites, primitive space rocks, believed to represent some of the oldest, least altered material remaining from the early solar system. If accurate, this comparison suggests that the water trapped inside lunar volcanic glass, and quite possibly a meaningful portion of Earth's own water as well, may share a common origin, delivered to both worlds by similar impacting material during the chaotic early history of the solar system, rather than the two planetary bodies developing their water supplies through entirely separate, unrelated processes. A third possibility, and one that has gained increasing attention among researchers studying the sun's interaction with airless bodies, involves the solar wind itself. The constant stream of charged particles flowing outward from the sun includes hydrogen ions, and when these ions strike the lunar surface directly, unprotected by any significant atmosphere or magnetic field, they can potentially react with oxygen already present in surface minerals, forming small amounts of water molecules directly on the moon's exposed surface over long periods of time. Researchers studying this solar wind process point to a particularly compelling piece of supporting evidence, gathered not from Apollo samples directly, but from more recent spacecraft observations of the lunar surface. Instruments capable of detecting subtle chemical changes across the moon's surface have observed water-related signals that appear to fluctuate with the lunar day and night cycle, weakening during the intense heat of lunar daytime and appearing to strengthen again during the extreme cold of lunar night. A pattern that fits neatly with a continuously replenished surface-level process driven by solar wind interaction, rather than a fixed, unchanging reservoir of ancient water trapped since the moon's formation billions of years earlier. Under this theory, at least some of the water detected in lunar samples might not be ancient material trapped since formation at all, but a much more recent, ongoing process, continuously replenished by the sun's own particles striking the lunar surface every single day. Untangling exactly how much of the moon's trace water comes from each of these sources, survived from formation, delivered later by impacts, or generated continuously by the solar wind, remains one of the active, unresolved questions in lunar science today. Different studies, using different samples and different techniques, have produced results supporting each explanation to varying degrees, and most researchers now believe the true answer likely involves some combination of all three processes, working together in ways not yet fully separated or understood. But the water discovery wasn't the only mystery hiding inside the Apollo 11 samples, and in some ways, the second one is even stranger. Alongside testing for water, researchers studying lunar rocks brought back by Apollo missions, including material from Apollo 11, also examined the samples for evidence of magnetism, specifically looking for signs that individual rocks had been magnetized at some point in their history, a property called paleomagnetism, essentially a frozen record of whatever magnetic field existed at the moment the rock originally cooled and solidified, and multiple lunar samples showed clear evidence of having been magnetized in the past. This should not have been possible, according to the understanding of the moon that existed at the time. Unlike Earth, the moon today has no significant global magnetic field. Earth's magnetic field is generated by a process called a geodynamo, created by the movement of molten, electrically conductive material within Earth's liquid outer core, churning and flowing in a way that generates a continuous magnetic field extending far out into space, the same field responsible for protecting Earth's atmosphere and creating the auroras. The moon, being far smaller than Earth, was long assumed to have cooled too quickly after formation to sustain the kind of active, long-lasting internal dynamo needed to generate a comparable magnetic field of its own. Yet the magnetized rocks brought back by Apollo 11 and later missions told a different story. Their magnetic signatures indicated they had cooled and solidified in the presence of an actual magnetic field, one strong enough and stable enough to leave a lasting, measurable imprint. If the moon never had a functioning internal dynamo capable of generating its own magnetic field, where did that magnetism come from? For decades, this question remained genuinely unresolved, and it still isn't fully settled today. One major theory suggests that the moon, despite its relatively small size, may have actually possessed a functioning internal dynamo for a surprisingly long stretch of its early history, potentially lasting anywhere from several 100 million years to as long as 1 billion years or more after its formation, generating a genuine, if likely weaker, global magnetic field, similar in basic mechanism to Earth's own, before eventually cooling enough for that internal process to shut down entirely, leaving only the magnetized rocks behind as evidence that it had ever existed at all. This theory gained significant support through later reanalysis of Apollo samples using increasingly precise dating and magnetic measurement techniques that allowed researchers to estimate not just whether a given rock had been magnetized, but roughly when and how strong that ancient magnetic field appeared to have been at that specific moment in lunar history. To measure this, scientists rely on the fact that certain iron-bearing minerals within a rock act almost like tiny natural compass needles at the moment the rock cools from a molten or partially molten state. As those minerals solidify, they lock into alignment with whatever magnetic field happens to be present at that exact moment, preserving that orientation permanently, essentially unchanged, for as long as the rock itself remains intact and hasn't been significantly reheated. By carefully measuring the direction and strength of this locked-in magnetism and separately determining the rock's age using radiometric dating techniques based on the slow, predictable decay of radioactive isotopes, researchers can build something close to a timeline, estimating not only that the moon once had a magnetic field, but tracing roughly how that field's strength appeared to rise and fall across different points in lunar history. Multiple independent studies found evidence suggesting the ancient lunar magnetic field may have been considerably stronger, for at least part of its existence, than scientists initially expected from a body as small as the moon, adding yet another layer to the puzzle, since a small, rapidly cooling body sustaining a dynamo that, strong for that long, strains some existing models of how planetary magnetic fields are generated and maintained. Some of the proposed explanations for this unexpectedly strong and long-lasting ancient field involve unusual internal conditions specific to the young moon, including the possibility that mechanical stirring caused by the moon's own changing orbital distance from Earth, combined with gravitational effects during its early history, may have helped sustain motion within its molten core for far longer than a simple, small, rapidly cooling body would otherwise be expected to maintain on its own. Other researchers have proposed that large impact events during the moon's early, heavily bombarded history may have periodically added extra energy into the core mantle boundary, temporarily boosting or sustaining dynamo activity that would have otherwise faded away much earlier. A competing explanation proposes that at least some of the magnetism found in lunar samples wasn't produced by an internal dynamo at all, but by external forces, specifically the intense, localized magnetic fields that can be generated briefly during massive asteroid or comet impacts. Under this theory, a sufficiently large impact striking the lunar surface could, in principle, generate a powerful but extremely short-lived magnetic field, strong enough to imprint a lasting magnetic signature onto nearby rocks in the immediate aftermath of the collision, without requiring any long-term internal dynamo process inside the moon at all. This impact-based explanation draws support from laboratory experiments here on Earth, where researchers have used powerful lasers to simulate the extreme conditions generated during a large impact event, vaporizing small target materials in controlled settings and measuring the brief, intense plasma clouds that result. These experiments have shown that impact-generated plasma can, under the right conditions, produce transient magnetic fields strong enough to leave a measurable, lasting imprint on nearby material, lending real physical plausibility to the idea that some of the moon's ancient magnetized rocks might trace back to specific violent impact events, rather than a slow, steady, planet-wide internal process. Some researchers have proposed a way to potentially distinguish between these two explanations by comparing the geographic location of magnetized samples to known ancient impact basins on the lunar surface, along with more precisely dating exactly when each rock became magnetized relative to known large impact events in lunar history. If magnetized rocks consistently cluster near the timing and location of major known impacts, that would lend stronger support to the impact-generated theory. If instead, magnetized rocks with similar signatures turn out to be more evenly and widely distributed across the moon's surface, regardless of proximity to any specific known impact site, that pattern would favor the internal dynamo explanation instead. So far, results from this kind of comparative analysis have been genuinely mixed, offering partial support for both explanations, depending on which specific samples and impact sites researchers examine, which is a significant part of why this particular lunar mystery has remained unresolved for so long. Both explanations remain seriously considered within the scientific community today, and much like the water mystery, many researchers suspect the true answer may ultimately involve elements of both processes. An early, genuine internal dynamo responsible for at least part of the ancient magnetic signal, combined with additional localized magnetism generated by specific, large impact events layered on top of it over the moon's long geological history. What makes both of these mysteries, the trapped water and the ancient magnetism, so remarkable isn't simply that they exist. It's that both were hiding, essentially undetected, inside samples that had already been sitting in laboratories on Earth for decades before anyone found them. Apollo 11 didn't just capture a moment in space exploration history, it captured physical evidence that, unknown to anyone at the time, contained scientific secrets that the technology of 1969 simply wasn't advanced enough to read. This is a detail worth sitting with for a moment because it reveals something important about how scientific discovery actually works. The moon rocks that answered these questions weren't gathered on some new mission decades later using more advanced equipment sent back to the lunar surface. They were the exact same physical rocks, the very same grains of dust that Armstrong and Aldrin scooped into containers during a rushed, historic moonwalk that lasted less than 2.5 hours. The information had been there, physically present, inside NASA's storage vaults the entire time. It simply took 40 years for instruments sensitive enough to actually read it correctly. NASA, recognizing exactly this possibility, made a deliberate decision from the very beginning of the Apollo program to preserve a significant portion of every lunar sample collected, sealing them away, untouched, specifically so that future scientists, armed with instruments and techniques that didn't yet exist, would eventually have the opportunity to study them again. It was, in a sense, a message sent forward through time, a decision that assumed science would keep improving long after the astronauts themselves had returned home, and that questions unanswerable in 1969 might eventually find their answer decades later, as long as the physical evidence remained carefully preserved and waiting. That patience paid off directly. Without those preserved samples, the water discovery in 288 and the ongoing paleomagnetic studies that followed would have been entirely impossible. There would have been no new lunar material available to test, no way to revisit the question with modern instruments, nothing left to examine except the original, decades-old conclusions. It's worth remembering just how deliberate this preservation strategy actually was. NASA didn't simply store leftover material out of convenience. Mission scientists specifically instructed that a significant portion of every return sample be sealed under carefully controlled conditions, protected from contamination by Earth's atmosphere and moisture, precisely because they anticipated that future scientific techniques, whatever they might eventually turn out to be, would likely be far more capable than anything available in 1969. It was an unusually forward-thinking decision for a program built under intense political pressure and tight deadlines during the middle of the Cold War, when the primary public focus rested almost entirely on the singular goal of safely landing astronauts on the moon and bringing them home before the decade's end, exactly as President Kennedy had famously promised. This also means the story of Apollo 11's samples almost certainly isn't finished yet. As laboratory instruments continue to improve, becoming more sensitive, more precise, and capable of detecting increasingly small traces of chemical and physical evidence, scientists will likely continue returning to these same preserved samples, asking new questions that couldn't even be properly formulated using today's understanding, let alone the understanding that existed when Armstrong first stepped off that ladder in 1969. Every few years, researchers submit new proposals requesting access to small portions of these carefully guarded samples, and NASA continues to approve a select number of these requests, always mindful of preserving enough material for future generations of scientists as well. In effect, humanity's supply of lunar material from Apollo 11 has become a kind of renewable scientific resource, rationed carefully across decades, with each new study adding another layer to a story that began the moment those samples were first sealed away in July 1969, long before secondary ion mass spectrometry, precise paleomagnetic dating, or any of the analytical tools that eventually uncovered these mysteries had even been conceived. It raises a genuinely fascinating possibility. What other secrets might still be sitting, unnoticed, inside the remaining Apollo samples carefully preserved in NASA's vaults, waiting for an instrument that hasn't been invented yet, and a question nobody has thought to ask before their true significance is finally understood? It's a strange thing to consider. Somewhere in a secure storage facility in Houston, sealed inside individually cataloged containers, sit pieces of rock and dust that a small handful of people have ever touched, gathered during a mission that lasted a matter of hours over half a century ago. And yet those same small, unglamorous fragments have already forced scientists to rethink long-held assumptions about the moon's formation, its history, and the forces that shaped it twice in ways nobody involved in the original mission could possibly have anticipated. Because that is really the heart of this story. Apollo 11 wasn't simply a triumph of engineering and courage, though it was certainly both of those things. It was also, quietly, an act of extraordinary scientific foresight, gathering physical evidence that would go on to challenge some of the field's most fundamental assumptions, not immediately, but decades later, once humanity finally built the tools capable of asking the samples the right questions. It is worth remembering that none of this was guaranteed. A less careful preservation strategy, a decision to distribute every last gram of material for immediate testing back in 1969 and 1970, or simple bureaucratic neglect over the following decades, could easily have left nothing behind for future scientists to re-examine at all. The fact that this story could even be told today is itself the product of a choice made by people who understood, even in the earliest days of lunar exploration, that some questions are only answerable by those patient enough to wait for the right tools to finally arrive. The moon, it turns out, wasn't nearly as simple, or as dry, or as magnetically silent as scientists confidently assumed back in 1969. And the proof of that had been sitting in storage the entire time, inside gray, unassuming containers of lunar dust, waiting patiently for someone to finally look closely enough to notice. What else might still be hiding inside those same containers, waiting for the next generation of instruments capable of finally reading it?